Hello, it's Keith here, and this is lesson 2 of the Yquest series of 6502 assembly programming tutorials. Now, in this series, we're going to be looking at this little Yquest game I wrote. It was originally a Z80 game, but it's been ported now to the 6502 systems, and today we're going to be looking at the BBC version, which you can see I'm playing pretty typically terribly here. The reason I chose the BBC as the first version to port is because the game was originally an Amstrad game, and the graphics of the BBC and the Amstrad have the same resolution and colour depth, so I thought it'd be a bit of fun to use that as the starting off point, as it were, for the 6502 version. Now, the game's maybe running a little bit slow here, I'm not sure, it's difficult to judge. The important thing to bear in mind is it's very easy to speed it up because there's a massive slowing down routine because the game's actually too fast by default. So the game's code isn't at fault if you think this is too slow. It's just that's the way I have configured it for today. So that's what we're going to be looking at today. Let's have a look at the source code and let's see how this version of the game works. Okay, so here is the BBC specific code, and we're going to go through each section of this and discuss how it works. So first of all, we've got definitions for the screen size here. The multi-platform code is all this common module that runs on all systems, but sometimes things like the collisions for the edges of the screen need to be reconfigured depending on the size of the screen. We've got some definitions to do that. The other problem we have is some of the systems are working at like the pixel level and others are working at the 8x8 pixel block level. I think the systems like the NES, the Super Nintendo, I'm just using the tile map at this stage. So we've not got much definition for showing our objects, but the internal logical definition is much higher. So the internal definitions might be thinking that two objects are overlapping, but the visual representation might not be showing them as not overlapping. And so to correct this, I have collision masks which I can turn on to remove some of the definition before doing the checks to check if objects are colliding. And because the BBC works when we write pixels, consecutive bytes of memory go down and then jump back up. So you've got 8 consecutive bytes going down the screen and then the 9th one jumps back up. So the horizontal definition is not too bad, but the vertical definition is very low. I'm working in 8x8 vertical blocks, you see. So to compensate for that, I'm using these collision masks here. We're then defining an area of memory for our definition, for our game definitions. User RAM's doing that. 0-page entries for our temporary registers. I use some 0-page entries to simulate Z80 registers. We've got our basic macros that are doing a lot of work for us. And the run location here is 200. Now, as I've said before, on the BBC, the code actually loads in at, I think, address 3000. But then I move it down to 200 because the screen's going to be around that area. So we're loading in down here and then we're relocating our code and then rerunning the code much higher up. So in this area we can have no calls or because the absolute addresses won't be correct. But when we get to this point here, the code is starting from its true memory location, and the running memory address when we get to this point will now be memory address hexadecimal 200, and that will give us plenty of memory for our code, and then at the screen which starts at around memory address 4000. So that's what we're doing there. That's why we're doing that. We're then setting up our screen here, including the colors. We're then clearing our temporary variables for our game definitions using the cldir command. This, like many of the commands, are in the basic functions. You can see that if I do cldir here. Here it is. So this is a simulation of the LDIR command, but it's actually clearing an area with zeros. So you'll see that in some cases for clearing the screen and things like that. So we're using it there just to clear the user RAM, and then our game will start proper. So here we're setting the lives to 3, the level to 0, we're zeroing the player sprite, and we're also turning off the sound here. Next, what we're doing is we're clearing the screen, and then we're going to show the title picture to the screen here. Now the title picture is in data defs, and the size will depend on the screen. We're using the biggest one here, this nice big chunky one here. That's going to be shown to the screen, and it's 1 byte per definition. Where's our code? Here it is. And so what we're doing here is we're reading in each byte from the source here. We're defining the source in HL. And if it's not a 0, we're going to show it to the screen. Now, what we're doing is we're calculating the sprite address. We'll see that later on. And then we are converting the XY position, because this is basically a tile number, and we're converting that to a byte position. So we're multiplying the X position by 2 and the Y position by 8 to get a byte position. And then we're using the show sprite to draw that to the screen, and we're repeating until we've drawn the entire screen here. Then we're showing a few text messages to the screen. I don't know if you remember, but we had a few text messages on the screen here. So that's effectively drawn this, and these are the text messages. The position of those will vary depending on the system. So in this case, we're putting them there. And then we are going to wait for the fire button. We're going to clear the screen, center the player, and we're going to initialize the level. So this is the start of each level and also the start of the game, just depending on the level number. The main loop, you can see, is just here. Now what we do is we have a temporary register, register X, which is going to store the directions the player's pressed, and we've got a delay here so we can slow or down or speed the game up by changing this delay. We then read in the controls, and if any keys have been pressed, we store that new change into the X register, so that once we get to the end of this, the X register will contain any key presses that were pressed during that delay. And we're going to store those in 0 page entry H here. We're going to use that later on. Now, when our main loop is occurring, we draw the text to the screen, we then clear the player object off the screen, and we are then going to check the key timeout. Now, if the player is holding down up, we want them to accelerate, but we don't want to accelerate as fast as possible because they'll lose control. So we have a key timeout, and if the key timeout is non-zero, we're going to skip over the direction keys. The direction keys are processed one by one here. You can see this is up, down, left and right. And in each case, we are changing the acceleration of Y or X here. And we've got these little functions here that are going to do that job of changing the accelerations for us. And that's in the multi-platform code, I believe. Here it is. So what these are doing is they are taking the IX pair and they're changing the value at that IX pair by 1, either incrementing it or decrementing it. And there's also one to negate it. And these are to change the acceleration as we require. So in this case, the player is holding down. So the acceleration, the Y acceleration is increasing. And in this case, they're pressing up. So the Y acceleration is decreasing. After we've done the Y acceleration, we do left and right with the X acceleration. That's what's going on there. We have a fire routine here, so the player can fire a bullet if they press the fire button, and we've got a configuration here for a second fire button, although I'm not sure the BBC actually has one, but if there is one, what we do is we stop the acceleration, so there's a kind of a handbrake stop there, which is quite handy on the systems that have it, but I'm not sure this one does as I've configured it here, but that's something we could maybe enable later. Once we've handled all the directions, we draw all of the objects on the screen. Draw and move handles all of the updates of the graphics and things, and we jump back to the top with this infinite loop here. So this will just keep going on forever, and this is what's actually doing the sort of game level. Now we've got a clear screen routine here. The screen is at 4180 and the screen size is 200 lines, 80 bytes per line. So we're just clearing the screen with that. Print chart, well, this is our new bitmap character drawing routine here. We've got a font defined in the same format as our sprites. We're taking in the accumulator the character to draw, so we're multiplying that by 16 because there's 16 bytes per character, and then we're adding that to the base of the font here. We're then using that as our source, and then we're calculating the byte position. Now there's 2 bytes per horizontal character, so we're multiplying X by 2, and there's 8 lines per Y character, so we're multiplying the Y by 8, and then we're using our show sprite routine to show the sprite to the screen. Then we're incrementing the X position. We're going to see show sprite in just a moment. Blank sprite will remove an object from the screen. We're getting the details of the object from the IX pair. Now we're checking the collision program because a collision program over 250 is a dead object that shouldn't be drawn and so shouldn't be cleared. But if it should be cleared, we're using the space within our bitmap font to clear it from the screen. We're jumping down here to do that. We'll see that in a moment. Get sprite address calculates a sprite memory address within the CPU memory for the sprite depending on a number, so that's passed in the accumulator. We're multiplying it by 16 because there's 16 bytes per sprite. We're then loading in the sprite frame. There are 4 banks of sprites and there's 16 sprites, so each bank is 256. So we're just loading the sprite frame into B here and the sprite number times 16 into C. We're adding that to the offset of the sprite bitmap, and then we are going to be ready to draw. If we are drawing from the sprite object, then we're going to load in the sprite number from the IX register, entry 0. We're going to load the X position from entry 2 here, and then we're going to load the Y position from entry 3 here, and we're just going to have to remove the bottom 3 bits of the Y position in this case because we can't actually draw easily halfway down an 8 pixel tall strip on the BBC because of the layout of the screen memory. Now if you were going to be clever you could write a better sprite routine than I have, but this is a simple example, so I didn't think that was going to be appropriate in this case, so that we're just using a simple one here. The show sprite routine is basically what we saw before in the simple series. We're calculating the memory address, we're then transferring all the bytes from the source to the destination, and we're repeating until we've done all of the lines here. So that's the sprite drawing routine. Get screen pause is the same as we saw before as well. That was in the simple series. I'm not going to cover it again. And the player read controls dual, I think, is basically the same as before. I think it might be slightly changed because we're now reading in from the joystick, the fire button, but other than that, it's not really any different from the simple series. We do have a wait for fire routine, which is re-randomizing the random number. Every time we read in from the random number, we're re-randomizing it. So we just do that and we wait for fire to be pressed and released. So wait for fire will just sort of debounce the fire button, and that's used sort of for starting a new level and starting the game, things like that. Finally, we've got the common definitions here that we need: a chibi sound to do our sound, basic functions, binary coded decimal functions, showing numbers to the screen, and a few other things here. We've got our font and our 4 banks of sprites here. So the font is the letters and the space, which is used to clear objects. And then we've got our 16 graphics for the game itself, the enemies, the player sprite, things like that. Finally here we've got the screen layout. This positions the screen sort of in the middle vertically, and we've also got the definitions of the colours here. I've chosen pink and green and white for this game. If you wanted different ones, of course, you could just change them. And that's really all there is to it. Here's just the final byte for the start of our code to work out how much to actually transfer. That's all that is. And that's really all there is to it. I mean, there's quite a bit of it, but it has created a reasonably passable game. You know, I think this is a bit of fun. So as I say, if you want to go ahead, you can download this game, and as I always say, you're welcome to try and make something better out of it. You know, maybe you can make a better game than I have. I'm sure there's lots you could do to this game to improve it, and even if you don't like this game, it was really just trying to give a demonstration of what a simple game looks like and how you can work with data structures and things to create arrays of enemies, things like that. Anyway, though, that's all I'm going to cover today. Hope you found this interesting. If you have, please like and subscribe, because people liking the videos really helps with the Google algorithm. They recommend videos by how many people like them. So if you liked it and you want other people to see it, please drop a like on it. Whatever you do, though, I hope you've enjoyed this. Thanks for watching today, and goodbye.